Om Namo Bhagavate Ramakrishnaaya. I offer my pranams to Maharaj here, Saurav Maharaj, and respected János Pach, respected Subir Ghosh, respected other faculty members of the department, and there are also faculty members from the other department as well. Warm welcome to you all. And we also have invitees, guests, students, not only from our institution, I also see students from other institutions as well, which is great. A warm welcome to you all on this scorching and sultry afternoon. All right, so now we are actually fortunate, privileged, honored to have amidst us a very great mathematician, one of the top mathematicians of the world, Professor János Pach. And incidentally, this is not his first visit. He has been here before. The last time he visited was 16 years ago, when this campus was still in its construction phase. So it's a rare opportunity for us, and you people as students are really fortunate to have him here, to hear him live. It's something which is of good fortune for all of us. So just to give a brief introduction of Professor Pach, I'll just read out a small introduction. Professor János Pach is now working with EPFL Lausanne in Switzerland and also with Rhein Institute Budapest. He obtained his PhD from Ortvász University. I hope I pronounced it all right. Hungary in 1981. And in his remarkable career spanning over 4 decades, he has received multiple international awards such as Grunwald Medal from the János Bolai Mathematical Society, the Ford Award from the Mathematical Association of America, and Rainy Award from the Hungarian Academy of Sciences, to name a few. He has been the program chair of several international conferences and symposia. He is co-editor-in-chief of the journal Discrete and Computational Geometry and serves on the editorial boards of several reputed journals, including Combinatorica, Siam Journal on Discrete Mathematics, Computational Geometry, Graphs, and Combinatorics. He has also authored several books and has over 300 research papers with an impressive citation count of over 15,000. So today's seminar, as you all know, is "And what if they are not perfect?" Sounds very poetic and makes the audience curious. But he will be talking about perfect and semi-perfect graphs and much more. As you can see, he's very informal, and feel free to ask questions at the end. So without further ado, I invite Professor János Pach to deliver his talk. Thank you.
Thank you very much. Thank you for the nice introduction. It doesn't matter because I will be walking up and down, so it won't help. So, yeah. So I should say that I feel, how did you say, honored and privileged, and there was something else. And happy, of course, most importantly happy to be here and to give a talk here. And it is true that I have been here in Belur earlier, before they even started constructing this university. And perhaps the last time I talked here, no, the first time I talked here, then everybody in the audience was in orange. Now I see only one, and two, I'm sorry. And so at that time I had to modify a little bit the content of my talk. Yes, so okay. So we'll see if you can hear me. You can hear me anyway, I guess, because usually I am. Yes, it is working. Usually I am louder than necessary. So, okay. So we know that nothing is perfect, not only this beautiful flower, which in fact is perfectly beautiful. But as I said, as it was said before in this talk, perfectness has a technical meaning, perfect graphs, and I will give all the definitions, and you shouldn't ask questions just at the end of the talk. Please ask me immediately when something is not clear, because if I lose you, then after that you can just leave and the rest won't be too interesting. So, okay. So let's start with the real content. So there is one picture that I wanted to show. These are two people who played an important role in this area, what I am generally talking about. This is Claude Berge, who was a French mathematician, one of the first people in graph theory, and he wrote the first textbook or monograph on graph theory, and in that monograph he introduced the notion of perfect graphs. And somehow this became a very popular area, and in the first 10 years of graph theory, half of the scientists working in this area worked on problems related to graph theory, so it had a big influence on the development of graph theory. And the second person is Paul Erdős, who was also one of the founding figures in graph theory, and he was less interested in the perfect graph things. He introduced probabilistic methods in graph theory, and had many other important achievements that are closely related to the subject of this talk, that what if they are not perfect. Okay, so now the first real thing, so notation, and I will be using this notation and terminology throughout all this talk. So if you have a graph, then let me draw one, which is, this is I don't know, for instance, this graph here, it has 6 vertices, and there are 2 parameters of this graph that are very important parameters, and they have been considered by mathematicians long before graph theory was born. The first one is the chromatic number. It's always, for whatever reason, if the graph is G, then this is denoted by chi of G. So this is the chromatic number. So this is that with how many, what is the smallest number of colors needed to color the vertices of the graph, so that every edge, if you look at the 2 endpoints of the edge, they are of different colors. So in this case, I have exactly 3 colors, in fact, and that's enough. So you can color this red. I am not sure if you can see that. This is too old, I think. And then these 2 points must be of different colors, I mean different from red, so maybe this is blue, this can also be blue. And I can use red for this one, but now I need a new color for this vertex, which cannot be red, cannot be green, because otherwise I would get a monochromatic edge. So I color it green. And then this vertex has a red neighbor and a green neighbor, so this must be blue. So I can do it with 3 colors. So the chromatic number of this particular graph, the chromatic number is 3. It is obvious that you cannot do it with fewer colors, because if you look at this graph, then it has a triangle. And the 3 vertices of the triangle must get different colors. So, and that's the other notion, which is denoted by omega, omega of G. This is called the clique number, or this is the size of the largest complete graph. So in this case, it is also 3. So one thing is clear, that the chromatic number is always larger than or equal to the clique number. Because if you have these 3 vertices that are mutually connected to each other, that's the definition of a clique. That how many vertices you can pick so that any 2 of them are connected by an edge. So if you have 5 vertices that are all connected to each other, then clearly you need at least 5 different colors. So in this case, the 2 numbers are equal, but in general, they are not equal. So if you look, for instance, if you look at this part of the graph only, and this is what you call G, you forget about the last vertex, then here, if this is a cycle of length 5, the chromatic number of this cycle is 3, but the clique number in this case is equal to 2, because there is no triangle, only 2 vertices that are mutually connected. So they are not always equal, these 2 numbers. And so we have many examples, actually interesting examples, of graphs where the clique number omega is equal to 2. So in that case, so if I forget about this vertex here, then the clique number is 2. But not only that the chromatic number is not 2, but the chromatic number can be arbitrarily large. It's not a difficult theorem, and there are many proofs of that. Actually, there are many proofs that are that prove far more general things, but there is not really a trivial proof that if you want a graph in which there is no triangle, so the clique number is 2, then you can build such a graph with arbitrarily large chromatic number, which requires a huge number of colors. And I show you one construction. Maybe later I will also indicate another one. So this is due to Zhikov, 1949. It's a very simple construction. So the construction is by induction. So you assume, so here is, for instance, a graph for which the chromatic number is 3. So, but there is no triangle. And assume that we have already constructed a graph Gn minus 1 in which there is no triangle, but it requires at least n minus 1 colors. In fact, it will turn out that it requires exactly n minus 1 colors. And from this graph, I define another graph, Gn, which will require n colors. So I have one which requires n minus 1 colors, and now I define one which requires n colors. How do I do that? So the way how I do it is the following, that out of the Gn minus 1, which I have already constructed, I take n minus 1 copies, n minus 1 disjoint copies. So the first one, second one, and then I do the following. These arrows are not important here. I just can forget about them because the graph is not directed. And now I do the following. No matter how I pick one point from each of those copies, I take a different point here on the right side, which is connected to exactly those points and nothing else. By this, I don't create a triangle because in order to create a triangle, two of those points, like if x1, x2, x is not a triangle because x1 is not connected to x2. These are disjoint copies. So there will be no triangles. The only thing that I have to prove is that the chromatic number of this graph is n. It requires n colors. Well, assume for contradiction that n minus 1 colors are sufficient. Okay, red, blue, n minus 1. So then look at the first graph that required n minus 1 colors. So, I pick coloring of that graph and I pick a point which is so this means that if there is an n minus 1 coloring of this graph GM is n minus 1 colors, then in particular it is a coloring of the first graph is n minus 1 colors. So I take a point in the first graph which is red. Look at the second copy. So a coloring of the big graph is n minus 1 colors would be also a coloring of the second graph is n minus 1 color. So this means that in the second one I can pick a point which is blue. So for each of the n minus 1 colors, I could pick a point in the first graph, in the second graph, and so on in the last graph, which have these colors. But now there will be a point x which is connected to exactly these points. And what color can that point get? It cannot be red because x1 was red. It cannot be blue because x2 was blue, and so on. So for this, I would need an extra color. This is the proof. And there are many other things, but I'm not saying that this is a very complicated proof, but it requires an idea. Every proof requires an idea. Also, it has a disadvantage that you see the Gn will be huge because for every choice of those vertices, I need to add a new point. So I grow the size of the graph as n grows. I grow it exponentially. So it's also an interesting question that what would be the smallest such graph, which has no triangle but requires n colors. Okay. Now, so now comes the definition of perfect graphs. So we call a graph perfect if actually these two numbers, the chromatic number and the clique number, they are equal. But not only if they are equal, because if you look at my original graph, this cycle plus this 1 point, then the chromatic number and the clique number are both 3, right, in that case. So they are equal. However, it has a subgraph for which the two numbers are not equal. Because in this subgraph, the chromatic number is the cycle of length 5, the chromatic number is 3, and the click number is only 2. So I call the graph perfect. It means not only that the chromatic number is equal to the click number, but it is also true for every subgraph of the graph. So if I look at the this 6 vertex graph, it wouldn't be perfect. But so you may wonder that are there any graphs that are perfect? And it turns out that there are a lot of graphs that are perfect. One example, for instance, which is a rather general thing. You don't have to remember that, but you see it in the literature often, chordal graphs. So chordal graph, it is the following. It has the property that if in the graph you find a cycle, and the length of this cycle is bigger than 3, so it's more than a triangle, then it also has another edge, at least one other edge. So here, for instance, you still have a cycle of length 5. This must also have another edge inside. So, for instance, this one. You still have a cycle of length 4. This must also have at least one other edge. So any graph which has the property that if you have a cycle which is not a triangle, then there is another chord in it, is called a chordal graphs, and chordal graphs are perfect. It's not trivial. Now, it turns out that there are many interesting classes of perfect graphs, and then this has been a question of Berge from the very beginnings. Berge was the guy on the left side to characterize these perfect graphs. And in fact, he had a beautiful conjecture that everybody wanted to prove, that, you know, if you look at a cycle of length 5, we have seen that this is not perfect because the chromatic number is 3, because try to color it by 2 colors, red and blue, then this is red, this must be blue. If this must be blue and I cannot use any other colors, then this must be red and this must also be red, which is a contradiction, right? So here we know that a perfect graph cannot contain a cycle of length 5. But the same argument you can also apply not only for C5, which is a cycle of length 5, this thing, but you can also apply it for any odd cycle, C7, C9, and so on. So if this was a cycle of length 7, then you would say the same argument. If this is red, then this must be blue, this must be red. So his conjecture was that a graph is perfect if and only if the graph doesn't contain any odd cycle. Moreover, the complement of the graph. So G does not contain any of these things. And the complement of G doesn't contain any of these. So what is the complement of a graph? The complement of a graph contains the non-edges of the original graph, right? So if you look at the cycle of length 5, for instance, what is its complement? Its complement contains all the edges that the graph does not contain. So it contains these edges, these. Actually, this is easy because the complement of a cycle of length 5 is also a cycle of length 5, just differently drawn, but it doesn't matter how I draw. There was some strange noise. Anyway, so this was the conjecture, that the graph is perfect if and only if the graph does not contain an odd cycle and its complement doesn't contain an odd cycle. And it was, in fact, there is a weaker, so if you look at this condition, then you see that this condition is symmetric. So what does it mean? It means that if it is true for the graph, then it is true for the complement of the graph, right? So, and that was called the weak perfect graph conjecture, and this was proved by Lovász, another Hungarian. So this was Lovász's theorem. This was really one of his most famous achievements when he was a young mathematician, that he proved that if G is perfect, then its complement is perfect, and vice versa. Which was like halfway towards proving the perfect graph conjecture. So, how can we prove that a graph is perfect? If you look at the graph, it may be a complicated problem, and it is maybe a complicated problem, especially because already to prove that to find the clique number of a graph is an NP-hard problem, computationally difficult. Now the technical definition is not very important. To determine the chromatic number is also a hard problem. So it would be very surprising if it were really easy to solve, to decide whether these two numbers are the same. In fact, for those who are interested in theoretical computer science, this is an interesting thing that which was proved, rather surprising, that it's not only difficult to find the clique number of a graph, but even to estimate the clique number of the graph by a huge margin is also very difficult. At any rate, the problem, even the strong characterization of perfect graphs, this was solved about maybe 15 years ago by Paul Seymour and Chudnovsky and I think that two other mathematicians. And this was considered one of the big achievements of discrete mathematics and graph theory. Okay, so there is one other example of perfect graphs that I'd like to show because they are very interesting and they are related to the rest of my talk. So for this, so now we know the definition of perfect graphs. Maybe I can. You remember that chi is always the chromatic number, omega is always the clique number, and if these two are the same, and it is also true for every subgraph of it, then they are perfect graphs. So one interesting class of perfect graphs is intersection graphs of segments along a line. Now, I should say that maybe I shouldn't have made this slide specifically, but it is an important thing, so I wanted to, because it turns out that this class of graph, intersection graphs of segments along a line, I will tell you in a second what they are also chordal graphs. And I said already that all chordal graphs are perfect. But here, this specific example I'd like to say. So what is the intersection graph? You can take your favorite geometric or non-geometric object. So in this case, in the first picture, you see segments along a line. In the second picture, you see rectangles. And what you can do is you can assign to each object, you can assign a vertex of the graph, right? To each segment over there, you assign a vertex, and you connect two of them if they intersect. So two segments, like 1 and 2, the blue segment and the red segment, the corresponding two vertices are connected by an edge because the two segments overlap, they intersect. Now, these graphs I call intersection. In the first case, it is intersection graph of segments, and if I am in the plane, this is an intersection graph of rectangles. 4 and 5 had a point in common, so 4 and 5 were connected by an edge. Now it turns out that intersection graphs of segments, intervals along a line, they are perfect. In fact, it is a good if you don't know that, then you are lucky, because it is a very nice sort of, I would say, high school contest problem to prove this. So let me write it down in case you want to think about it. So let's look at the segments. So let's look at intervals. Interval intersection graph. Okay. Segment. Okay. Segment intersection graph. So each segment is a vertex. Yeah. So what is the clique number of such a segment intersection graph? The clique number, omega g, in this particular case, omega g, so what does it mean? It means the number of segments that you can take so that any two of them intersect. So this is the maximum number of pairwise intersecting segments. Now it's very easy to see that if you have a number of segments and any two of them intersect, that all of the segments have a point in common. That's the only possibility. Actually, this is the simplest special case of what is called Halley's theorem. So I can say that in another way, this turns out to be equal, because of Halley's theorem, to the maximum number of segments that contain a point. So if you look at this example here, then there is no point of the line which is contained in more than 2 segments, right? So here the click number is 2. But if you have a triangle, the click number is 3, then the 3 segments have a point in common. Actually, Halley's theorem is a generalization of that. It says that if you maybe you heard that in 3 dimensions, for instance, it says that if you have a bunch of convex sets in 3 dimensions, and not any 2 of them intersect, but any 3 of them intersect, then again there is a point which is contained in all of them. So here, what I have said is just if any 2 segments have a point in common, then all of them have a point. So this is the click number. Okay? And then the chromatic number, it means that you want to color the segments with as few colors as possible, so that 2 segments of the same color, they don't occur. And this is a was observed first by Galai and Hajós, that these 2 numbers are always equal. And I give you a hint if you want to think about it. So not a solution, just a hint. So you look at your system of segments. So the proof will be by induction. And you look at your segments, there's a bunch of segments. You go from left to right and pick the segment that starts first. What does it mean that it starts first? So it means that whose left endpoint is the leftmost. In this case, the segment will be 1, because, and then you take the segment whose left end, the second segment whose left endpoint is the second, that's number 2, then number 3, 4, and so on. So you order, in this way you number the segments, and then what you can do is that so you pick the first segment that starts first, then it ends, and after that there will be another first segment that starts first, and so on. And then you look at it when it ends, and after that there will be another one, which will be the first one, which starts first. And all these segments colored by the same color. For instance, black. So this will be fine because no 2 black segments have a point in common. And then remove these segments. And it turns out that when you remove this segment, then omega will decrease by 1. And you can use induction. So this is the idea, but this is not a proof. It's just a sketch of the proof. Okay, so these are perfect, beautiful. But the problem is that if you go 1 dimension up, so you look at intersection graphs of rectangles, axis parallel rectangles like here, then it is obvious that they are not necessarily perfect. Because, for instance, these 5 rectangles, their intersection graph is a cycle of length 5. And we have seen that cycles of length 5, they are not perfect. Not only they are not perfect, they cannot be contained in any perfect graph. So just one side remark here, that why this kind of perfectness theorem had such a huge impact on graph theory, and in fact, a huge impact on optimization and also computer science. Because this was the first theorem among many beautiful theorems which are algorithmically very, very important of the following kind. So if you look at this thing, then the clique number on the right-hand side, you have something which is the maximum of something. How many vertices you can take so that any two of them are connected. On the left-hand side, you have a quantity, the chromatic number, which is the minimum of something. What is the smallest number of colors that are sufficient for coloring that graph? So these type of theorems are called minimax or max-min theorems. And it's a, I don't know how to say, an experimental fact, I should say, because it's not a theorem, or a meta-theorem, that whenever you find, for a class of graphs, you find such a minimax theorem, then there is an efficient algorithm for computing those things. So in general, there is no efficient algorithm for computing the chromatic number and the clique number. But for intersection graphs of segments, there is a polynomial time, very quick, very efficient algorithm for doing that, because there is this minimax. Okay, so here we have no equality. These graphs are not perfect, but the question is that can we measure it somehow? That, okay, they are not perfect, but they are still almost perfect, not so far from being perfect. So can we measure imperfectness? Because perfectness has a perfect definition, and we even know how to characterize perfect graphs. What about imperfect? And so this is the, let me skip this because I told you that already, just that those two important theorems, right? The characterization of perfect graphs. And then, since we have a characterization, it's not a minimax theorem, but since we have a characterization, actually, we can also recognize perfect graphs. You give me a graph, and there is an efficient algorithm. This was a consequence of the characterization of perfect graphs. That now we have a polynomial time algorithm, a quick algorithm. That if you give me a graph, I can tell you if it is perfect or not in polynomial time as a function of the number of vertices. Which in computer science, that's how we measure how efficient that algorithm is. But what if they are not perfect? And here come these two gentlemen who sort of, there must be something here. I guess that this is the router. So this is András Gyárfás and Jenő Lehel, next to their birthday cake. I think that they happen to have their birthday on the same day, or they just celebrate it together, I don't know. And they introduced a silly definition, and but that definition actually turned out to be very useful. And okay, so let me tell you what the definition is. If you wish, it measured that it introduced a definition that what it means for a graph to be not perfect but nearly perfect. How nearly? It's a big question, but let's not talk about it. So to repeat it, the definition of perfect graphs was that the chromatic number and the clique number are always the same, and even for subgraphs, the same. Now, I look at a class of graphs, not me, but János Pach and Leher, and they say that they didn't use this definition that nearly perfect, although I think that that would have been a much better expression for that. Instead of, they used an ugly expression, chi-bounded. You will see why, which is really an ugly term, and therefore it became widespread. Everybody's using the ugly term instead of something nice. So that definition was that, okay, they are not equal, but if I can find a function so that for every graph in the class, so look at a class of graphs like intersection graphs of rectangles or whatever. If in that class I can find a function so that the chromatic number is not necessarily equal to the clique number, but at least it is bounded from above by a function of the clique number, like at most 2 to the omega, or 2 to the 2 to the omega, or omega to the n, or omega log omega, doesn't matter what function. If you can find such a function, then you already say that the graph is nearly perfect. Of course, if the function is super exponential, then you would say that this nearly is not so nearly, but for instance, if instead of, you could say that the chromatic number is at most twice the clique number, then it is not so bad, right? Okay, it's not clique number, but okay. And then it turns out that there are several classes of graphs that satisfy this property, that are nearly perfect. So, in particular, the example I said, the intersection graphs of rectangles, it's not perfect, but nearly perfect. I think that yeah, I will tell you what the best result is. Or if you take intersection graphs of balls in any dimension, so instead of rectangles, you take in 10 dimensions, 10-dimensional balls of any radii, their intersection graphs. That's a big class of graphs. And in that class of graphs, there is a function so that the chromatic number of is at most that function. And although there are several geometric examples, not of intersection graphs, but disjointness. The definition is pretty clear that if you define disjointness graphs in the same way as intersection graphs, except that you join two vertices if and only if the corresponding objects are disjoint, not when they intersect, but when they are disjoint. And for those in disjointness graphs of segments, for instance, it is also known that they are nearly perfect. Okay. So let me tell you what is known here. Since I mentioned the intersection graphs of, oh, wait a second, you should shut me down when my time is up. So 6 minutes. Okay, because then it would be round. I can talk for hours and hours, and everybody will be happy. Yeah. So let me tell you what is for intersection graphs of axis parallel rectangles. So there it's not too bad. You see, the chromatic number is so big O. This means at most constant times the clique number times there is this log. The log is somewhat upsetting. I am not sure if it has to be there. I think it's an interesting problem. And actually, the same is true, even better bound, because instead of log, there is log square next to the omega. If you look at disjointness graphs, but in both cases, the conjecture would be that you don't need these log things. And I think that this is a beautiful open problem that maybe not hopelessly difficult. So to prove that if you look, for instance, at intersection graph of axis parallel rectangles in the plane, then the chromatic number of these graphs can be bounded by, say, 10 times the clique number of those graphs. And if you can prove it instead of 10, you can prove it by with 10 to the 10 to the 10 to the 10. Then from the point of view of theory, it would be equally good. From the point of view of practice, of course, it would be useless because the 10 to the 10 to the 10 to the 10 is bigger than the number of whatever electrons in the universe. So it's not a very... I think that the intuition behind that is that it is true for segments, and you would think that rectangles are axis parallel rectangles are really just you know, like direct products of two systems of segments, and it shouldn't be that different. I don't know. I mean, it's fairly easy to prove that there is a bound, like instead of omega log omega, it's not difficult to prove omega squared. To go down to linear, there is no reason why it wouldn't be linear. There is no, you know, there hasn't been any idea to prove a lower bound which would be bigger than the clique number. So maybe it is wrong. Maybe that's the problem, that everybody wanted to prove that instead of trying to come up with a construction disproving that. It's hard to tell. And there is another theorem that I wanted to mention, and then I will soon finish it, that you know, if you look at this example, you look at intersection graphs and their complement, disjointness graphs. And for both of them, you have very similar theorems and in fact the same conjecture, that they are nearly perfect. So János Pach came up with this conjecture that maybe if for a family of graphs, intersection graphs, they are chi-bounded, nearly perfect, then the disjointness graphs, it is the same is true. So here it is clear what was the intuition behind. Because the weak perfect graph theorem that I said, Lovász's theorem said that a graph is perfect if and only if its complement is perfect. So maybe it is also true that a class of graphs is nearly perfect if and only if the complements are nearly perfect. That's a very reasonable conjecture, and here is one example that if you look at disjointness, you don't read the question, just disjointness graphs of segments in the plane. We know that they are nearly perfect. In fact, the function is not that bad. The chromatic number is at most the fourth power of the clique number. In fact, it is an interesting unsolved problem to decide whether this. So probably you can improve this a lot. I tried because it is partially my theorem, but I couldn't. But you know you are young, you have better brains, so your chances are far better than mine. But then came the big surprise that actually it turned out that this was a bunch of students, Polish students, who proved 10 years ago, who came up with a construction of triangle-free graphs. This means clique number is 2, right? No triangle. Whose chromatic numbers are arbitrarily large. And these are intersection graphs of segments. So for disjointness graphs of segments, they are nearly perfect. But intersection graphs of segments can have arbitrarily large chromatic numbers. And that's a beauty. So this means that it doesn't, right? This proves that conjecture of maybe for axis pi, maybe for other. So it is hard to tell. It is hard to tell. Maybe there is some kind of other combinatorial property of these geometric objects that if you add, then already the two conditions are equivalent. I don't know. So there may be some theorem there which we haven't discovered yet. So I think that I already exceeded your patience, extended patience by 2 minutes. So this is the time to stop talking. So thank you very much for your attention.
Any question? So now, and then just to prove that
Oh, wow. This is beautiful. So are there any questions? Yes.
Balls. So can anything be said about the simple convex graphs, intersection graphs of convex, some convex sets?
Yeah. So segments are convex, right? And for them, they are not nearly perfect. Rectangles are convex. They are nearly perfect. So for intersection graphs of convex sets, they have some interesting properties, but not related to perfectness, because at least I don't know of any. So what is, I don't know how much graph theory you studied. There is something that's very interesting and very simple theorem that in fact one could teach in high school, is the Lipton-Tarjan separator theorem for planar graphs, which basically says that if you have a planar graph, then you can delete a small number of vertices so that it falls into two parts that are of roughly the same size, which is a dream for computer scientists, because the most effective method in computer science, if you want to run an algorithm, is that you remove something from your problem and you get two sub-problems that are smaller, and you somehow recursively. And then this works for planar graphs, and in fact there are infinitely many efficient algorithms for planar graph. And for those graphs that you asked, the intersection graphs of convex sets, there are similar theorems, separator theorem. So if you put something like intersection graphs of both or whatever, you can delete a few of them so that the system of convex sets falls into two parts so that there is no communication between left part and right part. And yeah, that's, but it's a very good question. I cannot really answer you. Yes. Anything else? So at any rate, I have a publicly available email address, which if you write down my name, then you can Google me. And if there is any question that occurs to you later, then I will be more than happy to answer.
Do you think this conjecture you mentioned, the students should, some students might should do?
Yeah, and in fact, yes, and I have, so I have special cases of this conjecture that are, so if you want, I can send it to you, and then you can distribute if someone is interested, and then, yeah, there are special cases that I am sure that are doable. Yeah.
Okay, here is something.
All right, if there are no more questions, then we proceed to the next
The flower.
presentation for them. A felicitation. So we request Professor Subhir Ghosh to hand over the presentation. Okay.
I don't remember the last time when I received flowers from a man.
So this whole, we have Professor Sukumar Adhikari, Dean of School of Mathematical Sciences. Presenting the book.
Thank you very much indeed. Yes.
Hungary. All right.
Thank you.
I want to say three things of this room. He is a very famous mathematician, wrote many important theorems and spoken problems. But two things which I found is very interesting about him. He travels a lot and still he produces a lot of result. Though he mostly stayed, his base stations are at one stage were Budapest, then New York, then Lausanne, and back to Budapest. But he has been traveling all over the places. One of the favorite place for him in traveling is India. He has come to Tiafa in my institute, stayed for months. He came to Calcutta. He traveled in the south, and he has been supportive to many of us in all in many matters. So he's a true friend of India. So I always consider him not only my personal friends, I also consider him as a true friend of India. And he has been interested in Indian philosophy, Indian art. He went to Bishnupur and he has been spending hours seeing the potteries and all those things. And he has a tremendous inclination to mathematics, not only in mathematics, but other areas of art, life, different kind of things. So I think he's a very broad man, open ideas, and all, most importantly, is very friendly and informal. Thank you, János, for coming here. And I'm sure the students have enjoyed. If somebody follows up with the conjecture, that will be happier. Okay. So he will be also speaking in ISI on Tuesday, not this Tuesday, but that is part of the workshop. Only some of you might be going there. Otherwise, he will be here on Monday and Tuesday in ISI Kolkata. In case you have anything to discuss, you can contact me and then we can find out some small time during the workshop and then
me say something else. First of all, thank you very much for these nice words. I think that if half of them were true, then yeah. Also, I mean, who isn't interested in India? Because India is infinite. So anyone who is interested in infinite, and all mathematicians are, is interested in India. But the other thing I wanted to say is to admit rather that I had two talks, one for today and one for this conference next Tuesday. Exactly. And one of them was for a broader audience, and the other one was more technical. And I thought that since I didn't know what my audience will be here, I was prepared that maybe all of them would be monks not interested in mathematics. No, this is an exception. You are. I didn't mean to. So my original idea was that the one which is for broader interest, I would stay here, and I will be more technical at the conference. But then I asked Subir about the audience, and I decided to change the two talks. So you got the hard work, and so if you also want to enjoy something lighter entertainment, then you can come to the mathematicians and computer scientists participating in the conference next week.
Okay, thank you. Thank you all. Maharaj, shall we move? Or you say something? Yeah.
First of all, I would actually thank Professor Subir Ghosh, because he is the person who organized this seminar for us. So please put our hands together for Subir Ghosh.
But almost it was washed out, because he writes to me, what time is my lecture in Belur? And 3 p.m. on Monday. But my flight to Dubai is cancelled. And I didn't say previous day. I said, when is your next flight? How are you coming? Then he says, Dubai, Dubai, lot of flood is there. So no flight. He was coming by air, so flight is there. So when I said, whenever we have a problem, we have only one algorithm. Pray to Thakur that he makes it. And he made it. So his flight was not cancelled. But when he reached Dubai, he sent a message to me. He said, no, I will make it. So then that's the thing. Right. So he has traveled so many places, but he always, except once, you made a mistake of a year, right? He was supposed to go in 1 year, some March or something. He went in the previous year to give a talk there. So such small mistakes he did earlier, right? Okay. So anything else? Okay. So.
Just a couple of announcements I have. So once you move out of the hall, we have refreshments. But before heading towards the refreshments, we have a photo session. So we'll just assemble outside and we'll take a picture with Professor János Pach. So thank you, sir, and we hope to see you again next time when you visit Kolkata. Thank you.
And then I'll put it in.